All right, so now we have problem 5 of homework 6. This one is pretty similar to the last one. It just has kind of a more complex mechanism. And then this part is a little different, this B component, because it is a welded collar. So if the rod tries to rotate like this, it will push up with a force couple here, causing a counteracting moment like this. So when we're drawing the reaction pairs, there would be the regular collar like perpendicular reaction force, and then also a force couple caused by that. So what we are trying to find is this couple M down at the bottom that is required to keep it in static equilibrium. And then we are also given these parameters just to fully define the problem. So we have theta equals 30 degrees and P equals 150 newtons. All right, so what I'm going to do is start by drawing the free body diagram for DBC. So member DBC. And what we can do here is we can actually do something really interesting where we define our coordinate system a little different than we usually would. So instead of doing the regular like x, y in this direction, we can actually shift the x and y like this, so that it is parallel with the rod here. So what that would look like is we kind of have our x direction along this rod. And then we'll also define our positive moment as counterclockwise. Okay? So the reaction forces that we have here, D is a collar connected to a pin. So it's just like in the last problem, we have no restricted moment because it can spin around the pin, and there's no restriction in the x direction at all. There's only restriction perpendicular to the direction of the rod. So we have this dy here, put it down here. And then we also have the load P that is given. And then at B, like I mentioned earlier, we have the regular perpendicular reaction here, and then also the force couple because it's a welded collar. So we have moment or couple MB, and then this B reaction force. Okay, now since our coordinate axes are shifted, when we do something like a sum of forces in the x direction, we have to account for that shift in our forces. So the x direction is along this. So if we draw out the rod, how we would normally look at our x direction, it would look like this, right? And then in this case, our x direction is in the normal, or you know, the more common, like just flat direction. And I'll actually keep that there so it's clear. And then our forces would look like this, right? Our dy would be somewhere here, dy, and then our P force would be like this. All right? And the way that we can shift everything is we know that this angle here is 30 degrees. And so anything perpendicular is also going to be 30 degrees because it's like you shifted the whole axis. So if we draw a perpendicular line here, we know that this, which was along the y-axis originally, is going to be shifted by 30 degrees with the new y-axis. Or let me draw it this way, actually. So we know that that is kind of how the axes are shifted. And then if we go down here, we can see that it looks something like this. And our original dy, which I'll actually just call d because it makes it less confusing with our weird coordinate system, and our p, when we sum them along the x direction, and then, oh, I wrote this wrong as well. That would just be straight down since it's a 90-degree angle. Okay, finally, we have it all set up. So our d in the x direction is going to be d times cosine 30, which actually, I believe, oh, yep, I drew it in the wrong side. Okay, so it'd be like this, 30. So it would be sine 30. Okay, and then our px is going to be p times cosine 30. Okay, so now we can do our sum of f in the x direction, and that would look like a dx minus px, which is d sine 30 minus p sine 30 degrees. And then if we rearrange for d, we get that it is equal to, let's see, p sine 30 degrees over, oh my god, I keep writing this wrong, cosine 30, cosine 30 over sine 30 degrees. Okay, and then if we plug our values into that, we get sine 30 divided by sine 30. We get that our d value is 259.8 newtons. Okay, so now what we can do is we can take this entire mechanism and draw it as a rigid body. So we have something like this up to D here, and then this is A. Then we have our couple down here, and we have our D force upwards here, and then our P here. Right? And what we can do is we can take a moment about A to find this couple here, but we need to first figure out the kind of like the distances of everything, because they don't give us much to go off of. So we have this 80 millimeters here and this 100 millimeters here, and that's all they give us, except for this 30 degrees as well. So the way that we can figure out these distances, what we really need is this one, the moment arm, because we have the moment arm for P here. We just need this moment arm. So the way that we can figure this out is we can create a lot of triangles, or two triangles, that's not too many. One here, we'll say this is point B, this is D up here, and then from point B perpendicular down to point A, and this is a 90-degree angle, and then we draw a triangle here. So we know that this is 30 degrees, and since this is perpendicular right here, we know that this is also 30 degrees. And so since we have the 80 millimeter hypotenuse here, we can use just geometry to find the distances here. So this would be 80 millimeters times sine 30 for this distance, this side length. And then what we can do is we can find this one and subtract it from 100 to find this side length. And if you do all of that math, which I'll write out here, 80 millimeters cosine 30, and then 100 millimeters minus 80 millimeters cosine 30. What we get is that this side length is equal to 0.04 meters, or 40 millimeters. And then this one is equal to 60 millimeters. And then up here, we have 30 millimeters. And then using this triangle now, if we do 30 millimeters divided by tangent 30, because tangent is equal to opposite over adjacent. This is the adjacent side, so we want to find that. We move this over, divide by tangent. We get adjacent is equal to opposite over tangent, which is what we have right here. And so if we do that, we get that this side length is 53 millimeters. Okay. Now from all of this, what we want to find is the distance here, right? And so we have the total distance here, and then we have this smaller distance here. So if we subtract the smaller distance from this total distance, then we'll get our original D. And so we get 13 millimeters as our D. And then we can use that as our moment arm for our D force in our moment about A equation. And we get this equation here. So P is counterclockwise about A, so it's positive. So 100, I'll change to meters. So 0.1 meters times P. And then D is also counterclockwise here, so it would be positive, plus D, which is 0.013 meters times this D value. And then if you add, this is going clockwise, so you have to subtract that couple there. And then move it over to the other side. You get that M is equal to 0.1 meters P plus 0.013 meters D, which gives you finally negative 18.43 Newton meters. And that just means that not negative, positive. That just means that this is the same direction as this, which is in fact the negative direction as we defined it, as clockwise. And that's your answer.